All right, the first question. Let's just go over these real quick. I'm not gonna solve them, by the way. I'm just gonna give you some advice when we read these. So there are actually three, let me read it, 9 different cities. Okay, so these 9, by the way, these are 8, sorry. These 8 cities are the demand centers, and then we have 3 supply centers, right? So the electricity can go from these 3 suppliers to these 8 customers. And then the following table shows the major residential markets for CSUS and power generation, the annual demand, and the cost to supply electricity to each market from each power generation plant. Prices are in dollar per megawatt, right? So the demand, and then, yeah. So there is no, so these are distribution costs per megawatt. And then assuming there are no restrictions on the amount of power that can be shipped, that can be supplied by any of the power plant, what is the optimal solution to this problem? What is the total annual power distribution cost for this solution? In addition to optimal solution, provide the mathematical formulation and Excel model, spreadsheet model. So I'm just going to start by this question. How many decision variables do we have in this question? So you're always going to go decision variables, objective function, and then the constraint. So let's just verbally review them. Again, I'm not going to write or solve it, but how many decision variables do we have?
Is it 8?
You want to go to 8?
Or no? That's what I was.
I mean, so what is it? So just define it, and then we'll figure out how many later.
What was that?
Say it again, Jacob. Sorry.
I are the decision variables kind of having to do with the costs pertaining to the cities that are being powered by the main main power generation plants. So
it somehow pertains to the cost. Cost is the objective, I would assume, the total cost, right? So look, when you read this, what is the optimal solution to this problem? So there are no restriction on the amount. Let's see, what is it? Power to residential, its main power generation are located in D3, and the cost to, yeah. Assuming there are no restrictions on the amount of power that can be supplied by any of the power plant, what is the optimal solution to this problem? What is the total annual power distribution cost? In addition to the, okay, I'll make sure that at least for your exam to make it clear, like the decision that you're trying to make. But in here, let me just explain it again. So you have 3 distribution center or 3 suppliers. They have some capacity. Actually, in this part, assume there's no capacity. There is no restriction on the capacity of these guys. You need to satisfy this much demand for Seattle, for example. You need to send this many megawatts of power to Seattle. You can send it, you can supply this much of demand by any of these distribution centers. But the supply here is costly. So there are different costs. So it makes more sense if you have unlimited capacity for Seattle, it makes much more sense to send it from which one of these 3? Jacob, or Sam, say it again.
San Antonio.
San Antonio, why?
It's the cheapest.
It's the cheapest among these 3, exactly. So you want to go with the cheap. So the Seattle has a specific demand. You need to make sure to meet this demand, right? They have a power demand, so you want to make sure to send it. And then you've got three options, three origins, three suppliers. Now you want to go your best decision. When we say optimal solution, you don't have any other parameter other than the cost. So when you read this question, it should come naturally to you that we should be looking for the cheapest option, right? Which would be San Antonio, as Sam said perfectly. So for the next one, Portland, this is the demand. You want to make sure to send at least this much. But which one of these three options, San Antonio, Dayton, or LaBelle, which one of them you think are the best, which one of them is the best option for supplying power, electricity actually to Portland? Again, Sam, yes, San Antonio, exactly, yes. Because it's the cheapest among the three and so on and so forth, right? When you solve this, so, okay, now how many decision variables do we have?
9,
Why 9?
because there's 9 different cities.
So 9 different, I mean, it's actually 8. It's a little misleading. I have to change that. Let me just take a note. I need to change this from 9 to 8. There are 8 actually, but is it enough to consider 8 decision variable? So, and what is it? Can you define it, Sam, for me?
It's choosing which generation plant or which city is getting power from which plant based on the cheapest cost. Or would you do 8 times 3 to be 24 to account for each plant that you have the option of getting the power from?
Sure. So yeah. So when you say which city, that's not numerical, right? That's you're not looking for a number. You're looking for a name. So the way you're describing it is a binary type of decision. Is a binary set of decisions. So let's say for Seattle, we're not going to do this. We're going to go with continuous, by the way. But the way you described it, Sam, you want to know if you're going to send, you're going to supply Seattle by LaBelle, whether or not you're going to send distribution from LaBelle to Seattle, whether or not you're going to send distribution from Dayton to Seattle, whether or not you're going to send power from San Antonio to Seattle. So you're making 3 decisions when it comes to Seattle. Which one of these 3? But the problem with this one, with the way you're approaching the problem, is that you're not allowing the demand to be satisfied by more than one city. So you may actually be able to send, let's say this is your demand, this is the amount that you need to ship, you need to send to Seattle, but you can actually have 100 units, 100 megawatts supplied by LaBelle, 200 by Dayton, and the rest by San Antonio, right? I mean, in practice, you can actually, the power can come from different sources. They don't have to come from one source. So instead of just saying whether or not to supply by Dayton, for example, convert it and say how much of this demand to come from Dayton, how much of it to come from San Antonio, how much to come from LaBelle. Does that make more sense or less sense?
Yeah.
Yes. So now the decision, let me just open an Excel file. I think I have to write it. So now the decision is how much of this demand, or generally speaking, how much power, how many megawatts to be sent to Seattle from LaBelle, how many from Dayton, how many from San Antonio, right? 3 decisions for this one, 3 decisions for Portland, same decisions. How much to be supplied for Portland? How much to be supplied from LaBelle? How much from Dayton? How much from San Antonio? How much power to be shipped to San Francisco from LaBelle? How much from Dayton? How much from San Antonio? So on and so forth. How many decisions do we have to make?
24.
24, 3 by 8, exactly. 24 decisions to be made. So I just put it here, chapter 11, group activity 3, decision variables. How much power to be sent from each power plant. You've got 3 of them. 1, 2, 3. I just called them 1, 2, 3, but you can also go with their name from each power plant to each city, major city or demand center. And then you got 1, 2, 3, all the way to 8. So you got 8 of them.
Professor?
Yes, yes.
So is this a in-class activity or?
This is group activity 3.
Oh, okay.
Yes, group activity 3, and I'm trying to give you some general tips on how to approach it.
Okay, thank you.
Yeah, there is no group, there is no in-class assignment for this week, last week. Yes, so this is it. So how much power to be supplied or shipped or sent from each power plant? So you got 3 of them to each one of these cities, and you've got 8 of them. All right, so 24 decisions. You can call them X1, 1, X1, 2, X1, 3, X1, 8, X2, 1, X2, 2, X2, Dayton being the second, 2, let's say boys, 4, 2, 4, X2, 8, Park City, X3, 1, 3, 2, 3, 3, 3, 4, and so on, right? Okay, now what's the objective? Guys, this is group activity 3, question number 1. What's the objective function?
To meet the demand in megawatts.
Meet the demand. So meet the demand, actually, we assume that the demand has to be met. So that's going to be a constraint for us, not necessarily the objective. So it's going to be a hard constraint. We have to fix it. We have to meet the demand. But how do we evaluate? What's the criterion, Christian?
We're trying to find the optimal way to meet that demand to reduce our costs.
Total cost, exactly. Total supply cost, distribution cost is the objective. So let me write it here. Total, I'm just going to call those X, I, J, decision variables, and they're continuous variables. Continuous, the amount that you ship, the amount of power that you supply. Objective is the cost. Objective is, let me just write it here. Total distribution cost. And that would be, so you're gonna per megawatt that you send from LaBelle to Seattle, you're gonna spend this much money. You're gonna need to spend this much money. Now, how much money do you spend if you send X11 units? 370.54 times X11. Does that make sense? And then so on and so forth. You just go all the way to this one, 511.72 times X38. Supply center number 3 to city number 8. So, and then you can just simply write it down. So 370.54 X11 plus Let's go this way. 391.88 x 1, 2 plus all the way to 511.72 x 3, 8. That's the objective function. Guys, make sure to stop me if you're not clear on the cost, if you're not clear on the decision variable, because everything else, everything that comes after this, the solution, your interpretation, everything depends on your understanding of the decision variables and objective function. If you make simple mistakes afterward, it's not going to affect your grade significantly. As long as you understand the decision variables, as long as you write down the objective function correctly, you showed that you understood what is the objective function. If you make simple mistakes in writing, in the calculation, it's not, it's definitely going to affect your grade, but it's not going to be very significant. But these are the foundation. If you get these right, you're going to get a big portion of the credit here. All right, how about the constraints? So these are the three important parts of any linear programming, any optimization problem. You're making decision about something, so you need to know what. You need to evaluate, you need to be able to evaluate your decision. You need to say which, you need to have a criterion for defining the optimality. How do you say a decision is optimal? Or how do you say if a decision is better than another decision? You need to have an objective, a clear objective function, a linear objective function. And then you need to have a set of constraints. And what are the constraints here?
The demand.
You need to meet the demand, Sam, exactly. So the amount that you ship, the amount that you send, the power that you supply to Seattle need to meet the demand. So you want to send at least this much. So I would say constraints, the main constraints here are demand satisfaction. So you have 8 cities, let's say Seattle, X1, 1 plus X2, 1 plus X3, 1. So X1, 1 plus X2, 1 plus X3, 1. What does this tell you? The left-hand side here. What is it? X1, 1. X11 is the amount that you sell, that you ship or send from LaBelle to Seattle. X21 is the amount that you supply by, what was it? Dayton to Seattle. X31 is the amount that you send from San Antonio to Seattle. Now, when you take the sum of these three, that will give you the total power, electricity, that is sent to Seattle. So the total that is sent to Seattle needs to be greater than 734.47, which would be the megawatts required by Seattle, the demand of Seattle, right? So that's for Seattle. You need to just repeat this for all other cities. So you've got 8 of them. So X12 plus X22 plus X32 should be greater than or equal to 883.58. Last one, X18 plus X28 plus X38 should be greater than or equal to 644. And then once you get this is your formulation for the first part, for the first part A. Once you get this, you should be able to write down the spreadsheet model and solve it with no problem. And you should be able to answer all other questions. In reality, however, there are some restrictions on the supply as follows. Each power plant has a maximum capacity of 3,800 megawatts of power to be supplied. The company requires that the supply for power plant in San Antonio to be at least 20% of the total supply. Okay, given these realistic constraints, what is the optimal solution? What is the annual increase in power distribution cost that results from adding these constraints to the original formulation? How do we answer part B? So part A, you're going to go ahead and create a spreadsheet model corresponding to this formulation and solve it. So that's for part A. For part B, what you're going to do, is there going to be any change to decision variables or objective function?
No.
No, not really. Yeah, so it's just a matter of adding, exactly, Jake. It's just a matter of adding constraints. And we got 2 sets of constraints to be added. So for first one, each power plant has a maximum capacity of 3,800 megawatts. How do I write this one?
Would it just be the sum of the power put out by each power plant and then restrict it? Or
You got it, Christian, yes. For part B, so you've got for part B, add the following constraints to the model in part A. Add the following constraints to the model in part A. All right. And then, so each power plant has a maximum capacity of 3,800 megawatts. Like Christian said, we need to put a constraint on the total supply by each demand, by each supply center. So the total that the first supplier sends out will be X11 plus. So all the power, all the electricity that is sent by origin number 1 to destinations 1 to 8, that would be the total, that would kind of refer to the actual realized capacity of power plant 1. And we want this to be not exceeding 3,800. Right, so you want this to be limited. You want this to be, so in part A, we didn't have this limitation. So the answer could be very, very small compared to this one. Now you're setting an additional constraint that is gonna deteriorate your objective function eventually, right? Your cost, it's gonna add more cost. Now that you can't sell, for example, in here, the ideal scenario was to send these amounts from San Antonio for, let's say, at least for Portland and Seattle. Now, if San Antonio has limited capacity, you can't send everything from San Antonio. You have to put a limit on it. Maybe half of this can only come from San Antonio. So that means you have to send power to Seattle from more expensive resources, from more expensive sources. So that's going to add to the cost, right? So that's the consequence of having this constraint. And then same thing for the other one, X21 plus X22 plus ... X28 less than or equal to 38. I'm just going to put ... here. And then X31, X32, X38 less than or equal to 3,800. So just keep doing this for all 3 of the power plants. The company requires that the supply from San Antonio power plant to be at least 20% of the total supply. How do I write this one? San Antonio is number 3. So the total supplied by San Antonio is 33.1 plus 3.2 plus 3.3 plus 3.4 plus 3.5 plus 3.6, 3.7, and 3.8 eventually. So this is the total sent from San Antonio. You want this to be at least 20%. So now what should be the sign? Less than or equal or greater than or equal?
Greater than or equal to?
Greater than, you got it, Richard. Yeah, greater than or equal to 20% of what?
The total power.
The total power. And what would that be?
Would that be 3,800 times 3?
No, 3,800 times 3 would be the total capacity, not the total supply. So when it says total supply, it's used capacity that you're looking for, not necessarily the potential capacity that you have.
Would it be the sum of all the demands?
You got it, Richard. And some of all the demands, yes. And also you can, just to be safe, I would actually use all the decision variables. So when it says total supply, X11 is the supply from origin 1 to destination 1. Now, if you do X11 plus X12 plus X13 plus X18 plus X21 plus X22 plus X23 plus X28 plus X31 plus X32, so on and so forth, all the way to X38, that would be the total supply. But yeah, you got it. It's going to be the answer because of the way the model is set up, because you're looking for minimum cost. By the way, I should have added a minimum. Because you're looking for a minimum cost, definitely it's going to stay. The total supply is going to stay equal to the total demand. You're not going to supply more than the demand because you're looking for minimum cost. That was a good point, Richard. Yeah. So here I just put minimum total distribution cost, and here, yeah, it's safer because that's what this statement says. It says total supply, and this is the total supply, sum of Xij's. Or I can just put here sum of total supply is sum of Xij's. That's the total supply. Sum of Xij, sum on i's and j's, I 1, 2, 3, j 1, 2, 3, all the way to 8. And that's it. So this is one constraint. These are 3, 1 for each power plant. So you add those to the solver and solve it again, and then answer the question. You just need to compare the objective function for part B with objective function in part A. You expect the objective function in part B to be higher than, to be worse than the objective function in part A, because now you have added constraints that are gonna limit your capability of meeting the demand with the cheapest sources, right? So that's another observation here. In part B, if the power demand for boys increases by 200 megawatts, how much the optimal total cost will increase? How do we answer this question?
Sensitivity report.
Jacob, did you say sensitivity report?
Yeah.
Yes, you got it. You look at the sensitivity report. So which part of the sensitivity report do we look at?
The shadow cost, like the shadow prices of.
Exactly. Shadow price tells you the change in the objective function, which is actually the total cost, with respect to 1 unit increase in the right-hand side. So power demand for boys. Here we have power demand for boys. Here is the demand. Demand for Seattle, you will have another one for boys. So you're gonna go check the sensitivity report. You're gonna check the shadow price for this specific constraint, for the demand satisfaction constraint for boys. Look at the shadow price. You need to shadow price is per unit. Now the question asks for 200 megawatts increase. So 200 times the shadow price, it's gonna give you the increase in the optimal cost. There's one catch here, the 200 megawatts should be less than the maximum allowed, because you get a minimum and maximum allowed, like allowable increase, allowable decrease. So allowable increase, when you look at the row in your sensitivity report, allowable increase should be 200 or greater than 200 for you to be able to multiply 200 by the shadow price. Assuming that the total demand requested by cities can increase, which city's extra demand will be more costly to be satisfied? How do we answer this one? Let's say each one of them the demand can increase by 1 unit, by 1 megawatt. Which extra 1 megawatt from each one of these cities is more costly?
Whichever one has the highest shadow price.
Whichever one that has the highest shadow price. Richard perfectly said, yes. Just look at shadow price is the cost with respect to additional unit of demand here for this constraint. So it just tells you the answer to this question. You look at it, you look at the list of shadow prices for the demand constraint, whichever has the highest shadow price is more costly, is more expensive to meet the additional demand. Use shadow prices from, so basically that's it. Please search for alternative solutions by creating a scenario that forces 0 values in the optimal solution to take positive numbers without increasing the total cost. Provide your formulation or spreadsheet model. We didn't do an in-class assignment, but there is a video on Cougar Courses. This is actually part of the material that you guys are supposed to know right now. So what do we do for this part? There's actually a video on chapter 11. When you check the list of weekly material, you'll see searching for alternative solution for linear programming. After you solve, let's say after you solve part B, after you added this constraint, you're gonna change the objective function to the sum of 0 variables, the decision variables that took 0 in optimality, right? So the objective function is going to be sum of those. You want to minimize, you want to actually maximize it. You want to try to get positive values for those. You maximize sum of zeros, and then you add another constraint. So the constraint that you add is that you want the cost not to get any worse, right? So you would say the cost function equals the optimal value that you found in part B. So you want to keep the cost to the optimal level that you found in part B. And at the same time, you're trying to push the 0 values, there's 0 decision variables that took 0 to take positive values. Now, when you solve this new model, if you get a positive objective function, if you get a positive value for one of the variables that originally took 0, without worsening your objective function. The new solution that you found is a new alternative optimal solution. It's good as the previous one, but it's different, right? So that's really the idea. Did you get it? Do you? I mean, if I want to show you this, I have to solve the whole question, because for alternative, you need to have an original answer and an original model, and then you just need to add the constraint, basically change the objective function to a constraint, and then add a new objective function. The new objective function would be the maximization of sum of 0 variables in the original optimal solution. Hopefully, you should be able to capture that after watching the recording, and then when you get the optimal solution. It's pretty easy. There's no complication. Any question, any other question from this problem, chapter 11, before we move on to the next one? Nothing? Okay. All right. Next question. Chapter 12. This is actually a little easier. It's actually from chapter 12. It's a binary linear optimization problem, binary integer linear optimization problem, but I would assume it's shorter than the previous question. So after reading this question, let's actually read it together. So there is a budget of $3 million that they collected, and now they want to invest this money into 10 mutual fund alternatives. There are 10 mutual fund alternatives. And so the idea, there are some diversification and operational restrictions that we have to respect. But basically, we want to invest, we want to put this money down, we want to divide this money and allocate this money to 10 different options, to 10 different investment alternatives. And then using the following expected return. So we got the expected return, like projected return in the future. We want to determine the investment strategy that will maximize expected return. So we got the keyword here for the objective function, maximization of expected annual return. And then we would answer this one. What assumptions have you made in your model? How often would you expect to run your model? All right. So now you guys tell me, how many decision variables do we need to make? Or you let me know, like you tell me what are the decision variables, not just how many. You have a lump sum of money, you want to invest it into 10 options, 10 alternatives. What's your decision? What should be your decision? What is it that you're trying to decide about?
How much to put in each, what is it, in each
Alternatives. Yeah, each one of these mutual funds. Sam, you got it perfectly. How much money that you need to put, you need to invest in each one of these alternatives. So 10 alternatives, 10 decisions to be made. And these decisions are continuous. These are dollar amount of investment. So continuous. They can take this decimal values. But then when you read the constraints, later on, you'll see, let's say here, when it says at least one fund should be chosen from each fund type. So out of these three, at least one of these three, the value of investment should be positive, at least in one of these three. One of them should be invested. One of them, the value that you put should be positive for one of them. So that means there's another decision, which it's kind of obvious, you already know, but in order to be able to formulate your decision, for your constraint, sorry, in order to be able to formulate your constraint and add your constraint to your model, you need to add another set of decision variables. And those are binary decision variables. Does that make sense? So now for fund one, you need to make two decisions. First, whether or not I'm gonna invest in this. Second, how much, if yes, how much I'm gonna invest in this. Right? So you've got question 12, for example. That's the worst, okay. Yeah. It's not coming up as columns, but I'm gonna go ahead and five, 6, 7, 8, 9, and 10. Oops. One type. And then expected return. Okay. Control C now, bring it in here, paste, and now we can convert a text to column, fixed with, oops, back, delimited, and then space. Okay, we have gross. I should have done that. Let's just go back here. Gross and income, let's just convert it. Gross and income. Replace all. Okay, close. You don't have, you can actually type, guys. You don't have to.
I think you have to do it for stock and bond as
Stock and bonds too. Yes, thank you, Lavina. Yes, got it. Got it. Okay. Start. Let's just get rid of the spaces and then perfect. And then here, text to columns and then space and perfect. Okay. So here we have font types. So decisions now, guys, decisions. First decision you want to make is whether or not to invest. I just put invest. And if yes, how much? So two sets of decisions for each one of these funds, for each one of these mutual funds. All right. Objective function. What's the objective function? When you read the question, it says we're looking for something that maximizes the expected annual return. So objective function is maximum return, expected return. Now, how do I write this function? So for each dollar that I invest, I'm gonna get 5.42 cents. I'm gonna expect to get this much return, 5.42 cents. Now, how much I'm investing, it's still to be determined by the model. I don't know, but the value is gonna come here. So if I invest $100 here, 100 times 5.42 cents, it's going to be the, let's say, 542 cents, for example, right? If I invest 1,000, it's going to be 1,000 times this value. So that's how you get this. The amount of investment times the return of investment. Plus, so that's for fund one. So that's the money return that I get for investment in fund one. For fund two, amount that I invest in fund two times the return of fund two, plus so on and so forth. So you can do it for all 10 of these guys, or you can just do the sum product of the investment and the returns. You don't have to really divide them by 100, as long as if you have the same like the same dimension, that's okay. You're dividing or multiplying your coefficients by the same number. It's not going to change anything. It's not going to change your optimal solution. It's not going to change the optimal value of your decision variables. That's for objective function. We got the decision variables, objective function, and now constraints. So the first constraint you have is the budget. I think it's not in the bullets here, but it's important to note that you have a limited amount of money. You have a limited amount of money, and I'm just gonna say it here. So constraint one, like capital available, right? The maximum cap or the total capital that you have available, and that's how much? $3 million. So the total investment cannot go beyond this number. You can't exceed the maximum capital that you have available. So here you put, what do you put here? What's the left-hand side of this constraint?
Would it be sum of how much you invest in each mutual fund?
Sam, thank you. You got it. Sum of how much decisions, sum of the amount of investment. That would be your left-hand side. The total amount that you are going to invest should be less than $3 million. Next, no more than 20% of the total amount should be invested in any of one fund, any one fund. No more than 20% of the total amount should be invested. So 20% of the total amount, 20% of 3 million, total amount is 3 million that you have. Or you can actually, instead of 3 million, you can interpret this total amount as X1 plus X2 plus X3 all the way to X10, the total investment, actual investment that you put down at the end of the day, not necessarily the 3 million. And the reason I'm saying that is because we didn't put equality here. You can actually, if you want. And since this is a maximization of return, it's going to make sure to use up the money that you have. Sorry, less than or equal. But yeah, that's another thing you can do. Or you can just simply use 20% of the 3 million, assuming that this is your limit here. No more than 600,000 should be invested in any one fund. How do you write this one?
It would be X1 is less than or equal to 600,000 and then all the way down to 10.
You got it, Sam. Thank you. Yes. X1 less than 600,000, X2 less than 600,000, X3, X4, X all of them, 10 constraints. So that's a constraint set with 10 separate constraints in it, right? Perfect, thank you, Sam. Next bullet. No investment lower than 80,000. 80,000 should be made. If a fund is chosen for investment, then at least 80,000 should be invested in. Now that's your opportunity. By the way, guys, there's one thing we haven't got all the constraints. Like I said, sometimes you have constraints that are not explicitly mentioned, and you have to figure them out. Like this one, budget. It was just one number in the first line, and we should know that it should be included. Another thing is the relationship between these ones. How much cannot be positive if investment is 0? So you cannot have 0 here and 5,000, for example, or 50,000 here. This is not feasible. This is wrong. You can't have a decision of not investing in something and then invest 50,000. If this is 0, this has to be 0, right? So this is actually very similar to fixed cost type of problem. Fixed cost type of problem. These are considered mixed integer LP. Mixed integer LP. Why they're mixed? Because here you got a set of binary decisions. Here you got a set of continuous decision variables. Binary, let me just maybe change the color. Continuous. Here you get decimal numbers, here you get 0 or 1. So this is a case of mixed integer, and it's similar to the fixed cost type of problem. So for fixed cost, there is a relationship or connection. I don't know what I call it. I think I call them connecting constraints that you have to consider maybe before you write down other constraints. So connecting constraints. Do you remember from the fixed cost video, what was the connecting constraint? Anybody remember that? X continuous variable less than or equal to M, huge number, like a maximum number that X can take, times Y. Y being the binary. So in this case, how much or amount should be less than or equal to a maximum value that each one of these can be. We just said it here in bullet 1, 600,000. 600,000 is the maximum times Y. Y is invest or not. Yes or no, or invest or no. Invest, investment, or yes, no type of decision. Let's just put this yes, no type of decision, yes or no. Yeah, or invest. I don't know how to say it, but or you can call this Y and you can call this X and you get this. I don't have to really suffer here, but yeah, you can just put Y here. Amount less than or equal to, or basically I just put X1. So basically Xi, X1, this is X1, this is, sorry, this is, sorry guys, let me just update it. Xi, this is invest or not, this is Yi, this is Xi. Yeah, Xi less than or equal to 600,000 times Yi. So you actually, you can update the bullet 1 because this is more restrictive than this one. So this becomes redundant. If you have this, this is redundant. So now you can actually update this to y1, x1 less than or equal to 600,000 times y1, and you can actually get rid of this. So this bullet 1 is actually now the connecting constraint. You can update that. x1 less than or equal to 600,000. Y1, x2 less than or equal to 600,000, y2, and so on and so forth. So see what this does for x1. If y1 is 0, what happens?
The whole value is 0 because you're not.
X1, exact x1 is forced to be 0. If y1, see what this does. If y1 is 0, then x1 has to be less than or equal to 0. All right, so if you made a decision not to invest in x1, it forces, sorry man, less than or equal to 0, and then we have a non-negativity constraint, so it'll force x1 to be 0, exactly equal to 0. But if y1 is 1, x1 can be any number from 0 to 600,000. So it doesn't force anything, any value for that one. So it'll allow it to be freely changing between 0 and 600. But it forces it to be 0 if y1 is 0. All right, so that's really the objective here. Okay, so let me move on, guys. No investment lower than 80,000. So now this one, we have a minimum bullet 2, and I think these are the two challenging. After this, it should be super easy. You can easily capture the rest. Can any of you help me with bullet number 2? If you make a decision to invest, you have to invest 80,000 or more. You can't invest 50,000, for example. You can't invest 40,000. It has to be 80,000 or more.
So x1 has to be greater than or equal to 80,000.
If you say this, and I would assume you're gonna repeat this for x2, x3, all of them to x10. If you say this, if you add this, xi's have to be 80,000 or more, but it's not exactly what the bullet is saying, what the description of the question is saying. It says if you invest more than 80,000. But what you're saying, what this constraint is saying is that regardless of your investment decision, you invest 80,000. Jacob, you want to say something?
I was just gonna ask, would you add y1 again to the 80,000?
Exactly. You got it. Exactly. X1 greater than or equal to 80,000 times Y1. If Y1, now let's see what happens with this one. If Y1 is 0, X1 has to be greater than or equal to, sorry, if Y1 is 1, meaning that you made the decision to invest in fund 1, X1 has to be greater than 80,000. If Y1 is 0, X1 has to be greater than or equal to 0, which is obvious. We already knew that the amount of investment is a non-negative constraint. These are non-negative continuous variables. So that's redundant. So we already knew this. But what actually matters here, by adding the Y1 to the right-hand side, you're saying that if you make a decision, then X1 has to be. It just brings the conditional statement now. All right. And then after that, this is pretty standard. At least one fund should be chosen from each fund type. So you have the fund types. So between fund 1, 2, 3, bullet 3, between fund 1, 2, and 3, at least one of them should be chosen, right? So this would do it between y1, y2, and y3. These 3, you should pick at least one of them. There has to be an investment here. Between gross and income, y4, y5, y6, greater than or equal to 1. y7 and 8, greater than or equal to 1. y9 plus y10, greater than or equal to 1. Next bullet, no more than at least, no more than two from gross and income funds. Gross and income funds, there are 3 of them. You want to only invest in 2 of them. How do we write this one? Bullet 4.
Would
Jacob.
it be y4 to y6 has to be greater than equal to what? Greater than equal to 1, and then y4 to y6 has to be less than or equal to 2.
Less than or equal to 2, exactly. Either 2, 1, or 0. I mean, but 0 will not happen because of this one, because you already said that it has to be greater than or equal to 1. Yeah, exactly. So y, for bullet 4, you want to have y4 y4 plus y5 plus y6 less than or equal to 2. Bullet 5, investment in 5. 5 is conditional on investing in fund 10. So 10, you can invest in 5 if you invest in 10. This is a conditional constraint. One is conditional on the other one. Make sure to check the videos, guys. Make sure to carefully watch the videos and understand the different types of constraints. But here, what we want to have, let me just write it down. Why I said fund 5 and fund, or let me just write it somewhere else. Bullet 5. So this is what is happening. Fund 5 and fund 10. So there are 4 cases that can happen. You can actually invest in none of them. You can invest in both of them. You can invest only in 5 and not only in 10 and not in 5. You can invest in 5 and not in 10, right? So there are 4 cases that can happen with respect to investing in fund 5 and 10. Now, now the description of this question says you can invest in fund 5 only if fund 10 is chosen. So you can, whenever fund 5 is invested, only it's allowable if fund 10 is also invested. So this one is bad, is not acceptable based on, let's see if I have strikes. It's not good. Okay, so I'm just gonna, or maybe, All right, so we are just removing these case. We're ruling out this case. You can't invest in fund 5 without investing in fund 10. This is not acceptable. How do I write a constraint to rule out this case? Isn't it this? Y less than or equal to y10. Y10 cannot be less than y5 if that's the necessary condition. Right? And this is, by the way, called conditional constraint. Again, make sure to check the video. Conditional constraints, the one that is the important one, which is in this case 10, comes at to the right hand side here, and then the one that is like phase 1 and phase 2. You can't start phase 2 unless you started phase 1, right? So there has to there is a sequential constraint. There is a conditional constraint here. There is a serial relationship between different phases. So you can't invest, in this case, you can't invest in 5 unless you chose to invest in 10. This is how you write it. Phase 2 less than or equal to phase 1. So when phase 1 is 1, phase 2 can be 0 or 1. But when phase 1 is 0, phase 2 has to be 0, cannot take 1. That's the logic here. Hopefully you guys got it. Let's just wrap it up and then one. The total amount invested in pure bond funds, the last two, must be at least 50% of the amount invested in growth fund. The first three. The last two, the amount should be greater than or equal to 50%. So X9, X, the amount, plus X10 should be greater than or equal to 50%, 0.5 times the amount in gross funds, X1, X2, X3. Well, it's 6, X9 plus X10 less than, is set at least, right? 50% of X1 plus X2 plus X3.